Welcome back to Machine Design course. We will continue with fatigue failure theories. In this slide and coming slides, we will explain and emphasize on stress concentration. A notch can be a hole, a groove, a fillet, a sudden change in cross-section, or any gap to the smooth contrast of a part. So notches or grooves or sharp edges will create a stress concentration, as we already learned under static loads. But we also have a stress concentration under dynamic loads, and we want to see how we could take that into account, how we could calculate stress concentration factors. The notches of concern here are those that are deliberately introduced to obtain engineering features such as O-ring grooves, fillets on shaft steps, fastener holes, and etc. So any natural grooves or changes of cross sections that happens because we want to, let's say, add or attach one mechanical part to a shaft or any other mechanical elements. It is assumed that the engineer will follow good design practice and keep the radii of these notches as large as possible and reduce the stress concentration. So this is what we learned already, that we should make these grooves and notches and changes in cross-sectional areas smooth as possible. Why? Because it decreases stress concentration. So we should follow those engineering practices as we used to and as we learned before for the dynamic cases, for the fatigue cases. So nothing has changed from that regard, but now we should see how we could calculate anyway stress concentration after we follow those practices and policies and codes to decrease the stress concentration. Notches of extremely small radii are poor design practice, and if present should be treated as cracks, and the principles of fracture mechanics used to predict failure. So we don't know what is fracture mechanic. We don't study in this course and in this book. Okay, so just put that aside. It's beyond our knowledge, and it's something that should be avoided. For normal circumstances, we should avoid fracture mechanic. A notch creates a stress concentration that raises the stresses locally and may even cause local yielding. So it's very similar to the static case. A stress concentration where only basic loads were being considered, the effect of a stress concentration were only of concern for brittle materials. This is basically what we have learned for static loads. It was assumed that ductile materials would yield at a local stress concentration and lower the stress to acceptable levels. This is basically referring to the static loads. With dynamic loads, the situation is different, since ductile materials behave as of brittle in fatigue failures. Okay, so now we see that for dynamic loads or fatigue loads, ductile materials behave same as brittle materials. And for both of these cases, the stress concentration will be of importance. The geometric stress concentration factor Kt is for normal stress and Kts for shear stress. But both of these Kt and Kts are for static loads. These factors give an indication of the degree of stress concentration at the notch having a particular contour and are used as a multiplier on the nominal stress present in the cross-section containing the notch. Why we call it geometric stress concentration? Because it only depends on the geometry of the part. And again, these are used for static loads. Many of these geometric or theoretical stress concentration factors have been determined for various loadings and part geometries and are published in various differences. So you could have access to these factors, and we will see some examples, and we already had some example in past in references of the book, in appendixes of the book. Okay, so for our book, if you refer to the appendixes, you will see plentiful of KT and KTS geometric stress concentration factors for different geometries. For dynamic loading, we need to modify the theoretical stress concentration factor based on the knot sensitivity of the material to obtain a fatigue stress concentration factor Kf, which can be applied to the nominal stress. So what we need to do, we need to first calculate the theoretical or geometrical stress concentration factor, and then we need to take to account the knot sensitivity of the material. Why? Because basically opposite of static load, stress concentration factor, now fatigue stress concentration factor Kf also depends on the material, and material has some sort of knot sensitivity factor. We will explain what is that. Materials have different sensitivity to a stress concentration, which is referred to as the knot sensitivity of the material. So from now on, we are referring to dynamic loads. Knot sensitivity is something that we use for fatigue stress concentration factor for dynamic loads. In general, the more ductile the material, the less knot sensitive it is. Okay, so this is a general rule, but we will see how we could calculate that. Brittle materials are more knot sensitive. Okay, so anyway, you see that for static cases, we could ignore ductile stress concentration in ductile materials. But here we have to consider the effect of the material for both of the cases, and we see that anyway ductile materials are less knot sensitive. Since ductility and brittleness in materials are roughly related to the strength and hardness, low strength soft materials tend to be less knot sensitive and than high strength hard ones, or than brittle ones. Notch sensitivity is also dependent on the notch radius, which is a measure of notch sharpness. The notch radii approach zero, the knot sensitivity of materials decreases and also approaches zero. If not for the radius knot sensitivity of the material at radii approach zero, engineers would be at a loss to design parts able to withstand any nominal stress level when notches are present. Okay, so it will be more clear when it comes to the mathematical formula. Okay, so here we are going to calculate fatigue stress concentration factor, or KF. Okay, and you see in the formula we have KT, which is geometrical stress concentration factor, and we have Q, and Q is notch sensitivity factor. Nuber is the name of a scientist, made the first true study of notch effects and published an equation for the fatigue stress concentration factor. Cohen later revised Nuber's equation and experimentally developed data for Nuber constant needed in this equation. Peterson subsequently refined the approach and developed the concept of notch sensitivity Q, defined as below. Okay, so this is basically history of studies on notch sensitivity and fatigue stress concentration factor from different scientists based on theoretical and experimental experiments. So in this equation, KT is the theoretical or static stress concentration factor for the particular geometry, and KF is the fatigue dynamic stress concentration factor. The notch sensitivity Q varies between 0 and 1. Okay, so when Q is 0, KF is 1, and once Q is 1, KF is equal to KT. Okay, so it varies from 1 to KT. 1, it means that we don't have any stress concentration. Okay, and when Q is 1, it means that we have a static load, or the situation is similar to static situation. The procedure is to first determine the theoretical stress concentration factor for the particular geometry and loading, then establish the appropriate notch sensitivity for the chosen material and use them in the above equation to find the dynamic concentration factor. Okay. The nominal dynamic stress for any situation is then increased by the factor for tensile stress in the same manner as was done for the static case. So this is the nominal stress. Okay, so this nominal stress could be for even the mean value, or it could be for alternative or alternating value of stress. Same for shear stress. We have KFS, which is shear fatigue stress concentration factor multiplied by nominal shear stress. This shear stress could be either mean value of the shear stress, or could be alternating value of that shear stress. Note that in the previous equation that when Q is 0, KF is 1, and it does not increase the nominal stress in above equation when Q is 1, KF is equal to KT, and the entire effect of the geometric stress concentration is filled in above equation. Okay, now let's see how we could calculate Q, or notch sensitivity. The notch sensitivity Q can also be defined from Cohen Hardra's formula in the terms of Nuber's constant A and the notch radius R, both expressed in inches. The Q is equal to 1 divided by 1 plus square root of A divided by square root of R. R is notch radius and A is Nuber's constant. Or in some references, they call square root of A as Nuber constant. And of course, the Nuber constant only depends on the material property. So in this graph, you will see for steel and aluminum, for different type of steel and aluminiums, you see that how the Nuber constant is a function of ultimate tensile strengths. Okay, so once we know what is the material and what is the ultimate tensile strengths, then we could find the Nuber constant. And then once we have a Nuber constant and we have the notch radius R, then we could calculate the knot sensitivity factor Q, and then we could find fatigue stress concentration factor. Okay, so here you see that Nuber's constant also tabulated for steel in terms of ultimate tensile strengths. Once, for example, the ultimate tensile strength of steel is 70 KSI, then the Nuber's constant is equal to 0.093. Instead of using formula of that Q equal to 1 divided by 1 plus square root of A divided by square root of R, you could simply use these type of graphs that you have Q on the vertical axis and notch radius on the horizontal axis, plus you have bunch of curves, each represent, for example, steel with different ultimate tensile strengths. So let's say you have steel with the ultimate tensile strength of 70, then you will pick this graph, and then by having the notch radius, you could calculate Q. Then you need this Q to calculate the fatigue stress concentration factor. Same, for example, here for annealed aluminum. And same for hardened aluminum, that you could find Nuber's constant as a function of ultimate tensile strengths, or you could basically calculate or find Q based on these graphs. And just as a reminder, again, in the appendix of the book, you could find these type of graphs, which you could calculate geometric stress concentration factor or static stress concentration factor. Either you could use these graphs or formulas and tables. So for this one, for this specific geometry, when you have a fillet, okay, and the cross-sectional area is rectangular, then you could find A and B constant based on D over D ratio and plug it into this formula to calculate the geometrical stress concentration factor. Okay, you need that KT to calculate fatigue stress concentration factor. Here we have an example. It's a very easy example. I'm gonna leave that to you to calculate the fatigue stress concentration factor for this specific geometry at the fillet. So a rectangular step bar, similar to the one in the figure, is to be loaded in bending. Okay. Determine the fatigue stress concentration factor for the given dimensions. Okay, so you need also material. Do the calculation for steel, for anneal aluminum, and for hardened aluminum. Okay, for these three cases, what you could do and what you should do, first you need to calculate KT, okay, which is a geometric stress concentration factor based on the appendixes of the book, based on those graphs and tables you have for geometric stress concentration factor. Then you need to calculate notch sensitivity, and for that you need Nuber's constant. You have those basically tables that tabulate Nuber's constant against ultimate tensile strengths. Okay, so very easy to calculate it. I'm gonna leave the calculation to you. We will have again these calculations in coming examples which are more complex, but this one just focus on how to calculate fatigue stress concentration factor, and expect students to do the calculation by yourself. Okay, so we are still in the main topic of fatigue failure theories, but you might have noticed that so far we haven't developed any particular theory. As we did for static loads, we had von Mises theory, we had maximum shear stress theory, and for those were for the ductile material, and for the brittle material we had Moore theory. Okay, so we developed those theories for the static cases, but we haven't developed any theory so far for fatigue loads, for dynamic loads. I could say that so far you understood the fundamental of that, how to find the SM diagram, how to find fatigue strengths, or SF. Okay, fatigue strength. So we managed to find the fatigue strengths based on the SM diagram. And now you know how to calculate fatigue stress concentration factor. But so far we haven't developed any theories. Now we are moving to this topic by designing for high cycle fatigue. So what could we do to design a part for high cycle fatigue? We are now ready to consider how to apply all the information presented on fatigue failure in order to avoid it in the design of dynamically loaded parts. There are 4 basic categories that can be treated separately, although 3 of them are just a special case of the force or general case. We will also see the same general approach to the solution of all 4 categories. So we want to see what are those 4 categories and what is the general one. Okay, so here in this table you could see. Figure shows the 4 categories in the matrix. The column defines the presence or absence of mean stress. So when we don't have a mean stress, let's say we have a fully reversed stress, we have these categories, and once we have a fluctuating stress, or the mean stress is not zero, we have these categories. The fully reversed case has a zero mean stress, and the fluctuating stress case has a non-zero mean value. Both have alternating components. The rho defines the presence of applied stress components on only one or more than one axis. So if this is a uniaxial or multiaxial, the uniaxial case represents simple loading case, such as a pure axial loading or pure bending. So when we have, let's say, uniaxial stress, we have a category of 1 when the mean value of stress is 0. And we have a category of 2 when the mean value is not 0. Why the mean value matters? Because the mean value is somehow representative of static load, or is effect of static load. An alternating value of sigma is the pure effect of dynamic load. And we have a multiaxial stresses for the category 3 when the sigma m is 0, and category 4 when sigma m is not 0. So category 4 is the general case, and any of the other categories are special cases of the category 4. Okay, so we'll start with the first one, and we see how we could expand the theory to the others, and finally the general case. The multi-axial case is general and allows applied normal stress components on all axes in combination with applied shear stress on any face of the stress cube. In reality, the pure bending cases are rare in practice. More often, there will be some combination of multi-axial stresses on machine parts. Both the fully reversed and fluctuating stress cases are commonly encountered in practice. However, fully reversed uniaxial stress category is discussed first. So we'll start with the first one, uniaxial stress category. Designing for fully reversed uniaxial stress. We're going to start with the category 1, or the simplest one. The simplest example of fatigue loading is that of fully reversed uniaxial stress with mean stress of 0. Some common applications of this category are rotating bending of a shaft that supports a static load, or reverse torque on a shaft with large oscillating inertial loads, and a mean torque that is effectively 0 compared to those oscillations. The process can be described in a set of general steps. Okay, so we should follow these steps to calculate the safety factor. I could say, okay, so when we say we are going to develop a theory, that theory should give us safety factor as it did for static cases, as the von Mises theory, for example, gives us a safety factor and safe region. These steps might look complicated at the beginning, but when it comes to the example, you will see how smooth and easy it is to follow these steps. So I'm gonna go through steps once and quick, but I'm gonna leave that to you. Once we do the example, review these steps and understand them in more depth. First, determine the number of cycles of loading N that the part will experience over its expected service life. So for example, we have a shaft. How many number of rotations that shaft will go through in the whole of its life? Or at least, how much number of cycles we expect from that shaft to withstand the load without any failure. Okay, that number of cycles will be N. This is something that we should assume or should be given for our design based on our service life. Why do we need that? Because you remember SN diagram. We need to calculate the fatigue strength, that SF, and based on the SN diagram, we need that N. Okay, second, determine the amplitude of the applied alternating loads from zero to peak. Note that a static load on a rotating shaft causes alternating stress. So we need basically that sigma A. Okay. Remember, we are investigating fully reverse load. So it means that the mean value of the stress is zero. And we only need to calculate the sigma A or alternating component of the stress. Plus, there is another, I could say, important phrase that the static load on a rotating shaft causes alternating stress. We had this in basically fatigue tests. How we could put even cantilever or a shaft on simply supported beams, and how we could apply dynamic load. 3. Create a tentative part geometry design to withstand the applied loads based on the good engineering practice. So you need to assume some part geometry based on your design and proceed with that geometry and see if that geometry works. 4. Determine any appropriate geometric stress concentration factors at notches in your part's geometry. So you need to calculate those KT. 5. Choose a tentative material for the part and determine its property. You need to choose a part anyway for your design. So choose it and extract those material properties. 6. Convert the geometric stress concentration factor KT or KTS for shear, the fatigue stress concentration factor KF. So you need to calculate Nuber's constant and notch sensitivity, and finally calculate KF. 7. Calculate the nominal alternating stress amplitudes at critical locations in the part due to the alternating service load based on standard stress analysis techniques. Okay, so what you need to do, you need to find the nominal loads, nominal stresses. 8. Calculate the principal stress amplitudes for the critical locations based on their stresses of applied stress. Calculate the von Mises effect stress for each location of interest. So you need to calculate the more circle and based on that principal stresses and the von Mises stresses. 9. Determine appropriate fatigue strengths modifications factors for the type of loadings, size of part, surface, etc. So you remember those reduction factors, modification factors. So we need to find those and apply it to the fatigue strengths. 10. Define the corrected fatigue strengths at the requisite cycle of life N. So find the real fatigue strengths. 11. Compare the alternating von Mises effective stress at the most highly stressed location with the material's corrected fatigue strengths taken from the SN curve at the desired number of life cycle n. Well, calculate the safety factor for the design from the relation NF, which is the safety factor, equal Sn divided by sigma prime. What is this Sn? Sn is fatigue strength at the n cycle, and sigma prime is when misses effective stress at the most highly stressed location. Given the fact that the material was only tentatively chosen and that the design may not yet be as refined as possible, the result of the first pass through these steps will most likely be a failed design whose safety factor is either too large or too small. So when the safety factor is less than 1, it means for sure failure. When the safety factor is too large, it means that we don't have an optimal design, and we are even wasting material, or we are wasting space, and we need to refine our design. Iterations will be required to refine the design. So we need to do some iteration. Why? Because we had tentative geometry at the beginning. We had the tentative material at the beginning. We had assumed a number of cycles at the beginning. And if we play with those and change them, then we could end up having a nice safety factor, something that makes sense. 2 or 3 safety factor is something desired, or maximum 5. Depends on the number of uncertainties and or engineering model. Okay, this is an example of the book, and we'll go through that. It's quite a large example, but it will clear the materials that we learned so far. A feed roll assembly is to be mounted on each end on support brackets cantilever from the machine frame as shown. Okay, so you see that we have a cantilever beam here. The feed roll, okay, so we have a roll of, let's say, paper as going inside this, okay. The feed roll experiences a fully reversed load of 1,000 pound amplitude split equally between the 2 support brackets. Okay, so let's say we have 2 support brackets that holds that roll of paper from left and right, and we only show one of those support brackets here, the left one, for example. Design a cantilever bracket to support fully reverse bending load of 500 amplitude for 10 to the power of 9 cycles with no failure. So 10 to the power of 9 cycle means basically means 1,000 million cycle. Its dynamic deflection cannot exceed 0.01 inch. Okay, so we don't also want deflection of at the tip more than this amount. So you see what is the load is fully reverse load. It falls into the category that we have studied, category 1. The mean value of a stress is 0, and we only have alternating component of the stress. We could have 2 possible design. One is the simplistic design, and you see that here we have sharp changes. We don't have fillet, so the phatic there's a geometric stress concentration factor is high, KT is 2, or we could have a fillet and a stress concentration factor will be less, something between 1.1 to 1.5. And this is a better design. Plus, what is the surface quality for this one? This is a cheap, let's say, design, and we have a flat mill stock. This one, we have a machine with the fillet, okay, so has a better surface quality as well. Operating temperature is 120 degrees of Fahrenheit, and the space available allows maximum cantilever lengths of 6 inch. Okay, so we cannot have a length of more than 6 inch. We need to make some assumptions, and the assumptions are as follow. The bracket can be clamped between essentially rigid plates or bolted at its root. So we could have a cantilever beam. The normal load will be applied at the effective tip of the cantilever beam from a rod attached through a small hole in the beam, so as you could see on the picture. Since the bending moment is effectively zero at the beam tip, the stress concentration factor from this hole can be ignored. Okay, so this is a stress concentration factor at the tip of the beam, not at the root of the beam, not at the big support. Okay, and these are assumptions that we are taking. Given the small quantity required, machining of stock mill shapes is the preferred manufacturing method. The first two steps of the process suggested above, finding the load amplitude and the number of cycles. So we are going through those steps, okay? I strongly suggest you to have those slides in front of you once you are either watching this video, or if you are reading the slide, put them side by side and see how we are going through those number of steps. We will begin at the third step, creating a tentative part geometry design. Okay, so the number of cycle was given 10 to the power of 9. Yes. And we'll start from the third one. And we need to start from a tentative design. And we assume a geometry of B, the capital R, and A and L. And we said that L cannot be more than 6 inches. Then we need to choose a material, tentative material. Material chosen is SAE M40 normalized steel with the ultimate tensile strength of 80 KSI. Okay, then we proceed with those steps. The reaction forces and reaction moment to be calculated. So these are the reaction forces and moment at the base of the cantilever beam. Very easy to calculate them by writing sigma f equal to 0 and sigma m equal to 0. Area moment of inertia of the cross section, distance to other fiber, and the nominal stresses are the other steps that should be done to calculate the nominal alternating stress. Okay, so I and C are calculated. And then we already had this formula that sigma is equal to MCI. Okay, M here is alternating components of bending moment. Okay, so once this M or the bending moment is alternating, so the stress we are calculating or is also alternating stress. Why we call it nominal? Because it's purely based on formula and we haven't applied any stress concentration factors so far. We have MCI, we plug it into the formula and we calculate the sigma A nominal. Now we need to find the Kf. First, find the geometric stress concentration factor Kt based on the appendices in these graphs. So D over D ratio and R over D ratio, and we could basically interpolate to find the A and B constant. Once you have A and B constant by interpolation, then you could calculate Kt, or you could also approximate it from the graph, and you should end up with similar number. So this is Kt. How we could find Kf? To find Kf, we need to calculate the notch sensitivity Q of the chosen material, and it's calculated based on its ultimate strength and the notch radius. So from the table, SU is A kpsi and numerous constant, so 80, and numerous constant will be 0.08. Once you have a numerous constant and an R, which is a given or was assumed, those are tentative number that we assume at the beginning, then you could calculate the notch sensitivity factor. Now you have the notch sensitivity factor, then we could proceed to find the fatigue stress concentration factor. The value of Q and Kt are used to find the fatigue stress concentration factor Kf, which is in turn used to find the local alternating stress sigma A in the notch. So Kf is equal to 1 plus Q multiplied by Kt minus 1. If we plug all the numbers that we found already, then we could find Kf. We calculate the sigma A nominal. If you multiply it by Kf, then we could find the real alternating stress, or sigma A. Okay, so now what should we do with that sigma A? Very similar to what we did in the von Mises theory. First, we need to find principal stresses. Okay, so we need to find principal stresses, sigma 1 and sigma 3. So either from the formula or from the Mohr circle, practice it by both of two methods, and you should end up with the same number. And if you do so, then you could find sigma 1 and sigma 3 alternating value. Okay? So sigma 1a and sigma 3a. So this is alternating principal normal stress. Once you have these numbers, then you could find von Mises effective stress sigma prime to calculate the alternating effective stress. Just you need to plug these numbers, and then you have the sigma prime. Okay, so now we don't know what is the fatigue strength, and we need to follow some steps to calculate the fatigue strength. To do so, we need to first calculate the uncorrected endurance limit. Why endurance limit? First, because our material or assumed material is steel, and the number of cycle is more than 10 to the power of 6, or 1 million cycle. So then we have endurance limit. So the uncorrected endurance limit, based on the formula we have for the steel, is half of SUT. Okay, where this formula is coming from, just as a reminder from this set of formulas. And since the SUT is less than 200 KSI, then we chose this formula. Now we should apply correction factors. And we had 5 or 6 correction factors that we need to calculate one by one. The first one is size factor. Or this rectangular part is determined by calculating the cross-sectional area stress above 95% of its maximum stress and using that value to find an equivalent diameter to find C size. For D between 0.3 and 10 inch, C size could be calculated by this formula. And then we could find A95 and D equivalent and use that D equivalent to plug it into this formula. Where these formulas coming from previous slide and lectures. Okay. Now for the surface, C surface, we could calculate it based on this equation. So we need to find the A and B constant. And based on the table, since we are a machine or cold rolled surface material for American units, then we have these A and B constants. And then we have ultimate tensile strengths, and we could find then C surface. The next will be for the loading. Since the loading is bending, the C load is 1. Temperature is 120 degrees of Fahrenheit. So based on this formula, C temperature is 1. C reliability, we're going to go with the 99.9 reliability. This should be in your assumption or basically givens of the problem. And then we have this C reliability. Now we have these all of these 5 reduction factors or correction factors, and we could find the corrected endurance limit or fatigue strength. This endurance limit here is fatigue strength. So we multiply all of them to the uncorrected fatigue strength, which is equal to the uncorrected endurance limit, and we see that the SE will be equal to this number, which is only 29% of SUT. So we cannot use 80,000 SUT as we had. We must go through these steps to calculate the fatigue strength. Fatigue strength is always less than ultimate tensile strength. Okay, now we have everything to find safety factor. And that safety factor is equal to the fatigue strength divided by effective stress and is 0.69. So unfortunately, is less than 1 and the beam will fail. Since the deflection also is important to us, you could either use a singularity function to calculate the deflection, or you could refer to the appendix of the book to see for a concentrated force at the tip of a cantilever beam, what is the formula for the deflection, and you could calculate the maximum deflection of the tip. And you see even this one exceed our limit. So what should we do? We should back to the first steps and change our tentative geometry and material. There is no other way around. Okay, so here you see that we are going through iteration. This table shows us the first iteration, and we ended up with the safety factor of 0.69 and a deflection of 0.026. These are based on these geometries that we assume at the beginning and the material. Now we could go with different geometry, and if we change those geometry and make them bigger, okay, then we could have a safety factor of 2.5, which is desired, and the deflection, which is less than 0.01, half of that almost. And it falls into or basically design a specification, and we could say, okay, safety factor is more than 1 and is under 5, so is reasonable, so it doesn't fail, plus it doesn't deflect too much. So those geometries are desired and good enough for us. So the final dimensions are B, D, I, R, A, and L as given here. Safety factor will be 2.5 and the maximum deflection is half of 0.01. These are both satisfactory. Note how low the fatigue stress concentration factor is at KF 1.16. Okay.